In the previous video, we saw that the autoionization of water is an equilibrium that can be expressed in terms of Kw, which was equal to the concentration of hydronium in solution times the concentration of hydroxide. And again, we said this is a constant, and that the constant has a value of 1.00 times 10 to the negative 14th. Now, let's consider that we have pure water. If we have pure water, that means every time a molecule or an ion of hydronium is produced, we'll also be producing hydroxide. So at any given time, the amount of hydronium that's present in solution must be equal to the concentration of hydroxide in that solution. And what I'm going to do here is I'm going to set both these values, since they're equal to one another, equal to x. Okay, so that means that x times x equals 1.00 times 10 to the negative 14th. Okay, so we get x squared equals 1.00 times 10 to the negative 14th, and we can take the square root of both sides here, and we get x equals 1.00 times 10 to the negative 7th molar, which equals the concentration of hydronium, which we said is the same as the concentration of hydroxide. Okay, now this is for a neutral solution. When I say neutral, that means no acid or base has been added. This is just pure water. So when we have a neutral solution, what that means is that the concentration of hydronium is going to equal the concentration of hydroxide. Okay, but there's going to be other possibilities. We might find ourselves in a situation where the concentration of hydronium is greater than the concentration of hydroxide. Or we could have a situation where the concentration of hydronium is less than the concentration of hydroxide. So when we have more hydronium present than hydroxide, we say that that is an acidic solution. And if the concentration of hydronium is less than the concentration of hydroxide, that's going to be considered a basic solution. Another way of looking at this is that when we have an acidic solution, the concentration of hydronium is going to be greater than 1.00 times 10 to the negative 7th molar. And therefore, the hydroxide concentration must be less than the 1.00 times 10 to the negative 7 molar. Whereas in the case of a basic solution, the concentration of hydronium is going to be less than 1.00 times 10 to the negative 7th molar, and the concentration of hydroxide is going to be greater than 1.00 times 10 to the negative 7th molar. Now here's the problem. Dealing with numbers like this in scientific notation, where we're talking about decimal points that are 7 digits to the left of the first number, that's kind of tricky to wrap your brain around. So it's nice to have a more succinct system, okay? And that succinct system that we're going to use is called the pH scale. Okay, so the pH scale takes what is an otherwise very broad range of possible values that we could look at in terms of concentrations to determine whether or not something's acidic, and it condenses it down to a scale that goes from 0 up to 14. Okay, so right here in the middle, we have a pH of 7, and that is considered neutral. Okay, anything that shows up between 0 up to 7 is considered acidic, whereas any solution that has a pH between 7 and 14 is considered basic. Now, how do these numbers relate to the concentrations of hydronium and hydroxide? Well, we can calculate the pH of a solution by taking the negative log of the concentration of hydronium in solution. Incidentally, you might also see it written as pH being equal to the negative log of the concentration of H plus in solution, and they mean the same thing. Okay, so they can both be utilized equally. So let's say that we have a solution that is 0.0010 molar in HCl. Okay, remembering that HCl is a strong acid and is going to dissociate completely. That means that our concentration of hydronium is going to be the same. So to calculate the pH, we simply take the negative log of 0.0010, and what we wind up with, let's see here, is going to be 3.0. So we can see fairly immediately that this solution is going to be an acidic solution, which of course we already knew it would be because we took hydrochloric acid and put it into water. But there's going to be some cases where it's not going to be quite so easy. Let's consider a solution where we have a concentration of, actually let's use scientific notation here to make this a little easier to look at. 3.80 times 10 to the negative 7th molar HCl. Okay, so now what we do is we again assume that the concentration is going to be equal to the 3.80 times 10 to the negative 7th molar for the hydronium. So the pH will then be equal to the negative log of that. Okay, and we get 6.42. And you can see here, as the concentration of the acid is getting lower and lower, the closer we get to being neutral in pH. Now this raises an interesting question. What if I had a solution that was a basic solution? So let's say the concentration was 0.0010 molar sodium hydroxide. Okay, we want to know what the pH is. Well, the first thing that we're going to have to do here is we're going to have to figure out what the hydronium concentration is for this solution. Okay, so we remember that Kw is going to be equal to the hydronium concentration times the hydroxide concentration, which is equal to 1.00 times 10 to the negative 14th. Okay, so we can find the hydronium concentration by taking 1.00 times 10 to the negative 14th and dividing that by 0.001, and what we wind up with is 1.00 times 10 to the negative 11th molar. Okay, now we can plug this into our pH equation. So pH is going to be equal to the negative log of the proton concentration, or the hydronium concentration, which is 1 times 10 to the negative 11th molar, and we wind up with 11 as our answer. And that number kind of makes sense. Okay, on the pH scale, this is definitely on the basic side of things, which is what we would expect to see for a basic solution like that of sodium hydroxide. Now you might be questioning, why is it that we pay so much attention to hydronium concentration? Why isn't there a pOH scale? And the answer is there is. Okay, there is a pOH that we can calculate. It's just not used quite as often. But the pOH, as you can imagine, is equal to the negative log of the concentration of hydroxide in solution. Okay, and if you look at the previous example that we just did here, we can do the calculation and plug in the concentration of hydroxide directly. And what we wind up with is a pH equal to 3. Okay, I'm sorry, pH, a pOH that is equal to 3. Now, notice that when we take 3 and add it to 11, we get 14. And that's actually a very useful relationship that we can invoke. Well, we're going to evoke it quite a bit. The pH of a solution plus its pOH is going to be equal to 14. So if we have a solution where we are given the hydronium concentration, we can use Kw to figure out the hydroxide concentration. And we could use that to figure out the pOH. Okay, or we can use the hydronium concentration to directly figure out the pH. Okay, so that's how we would find both the pH out and the pOH. But we have to remember that if I know the pOH, then I can use this relationship right here to come up with the pH. And likewise, I can use the pH to figure out pOH. Okay, so there's a number of different paths that we can take to get to various data points. Okay, so it's just important to remember that there's all these different ways of doing this. Okay, so if we have an acidic solution, okay, we're going to be given the hydronium concentration. Okay, so this is a solution like 1 molar HCl or 0.01 molar not sulfuric acid, nitric acid, something like that. Okay, I can take this and use the equation for pH to directly come up with the value for pH. Okay, but if I needed the pOH, I can take that pH value and subtract it from 14 to get pOH. Okay, that's the fastest way to do that. Okay, if we have a basic solution, okay, that means we're going to be given the concentration of hydroxide. So 2 molar sodium hydroxide or 0.3 molar potassium hydroxide. Okay, we can use that to find our pOH, which can then be used to calculate the pH. And the bottom line here is whether a solution is acidic or basic, we can find both the pH and the pOH for that solution. Now we see here that we can go from concentration to pH and pOH, but we can also go from pH back to concentration or pOH back to concentration. And to do that, we just need to take advantage of some of our logarithm rules. Okay, so we know that pH equals the negative log of the concentration of hydronium. Okay, now how do we solve for hydronium concentration in this equation? Well, first thing we do is we multiply both sides by -1. Okay, and then to undo the log, what we do is we raise 10 to the power of the logarithm. And we have to do the same thing to the other side. Okay, so what we wind up with is the concentration of hydronium equals 10 to the power of the negative pH. Okay, and that's going to be our concentration. We can do the same exact thing with pOH. pOH is equal to the negative log of the concentration of hydroxide. Okay, so the concentration of hydroxide is going to be equal to 10 raised to the power of the negative pOH. Okay, so these are very handy formulas to have at your disposal when you're trying to convert back and forth. And what this also means is that, if you're given the pH of a solution, okay, you can use that information to figure out the hydronium concentration. And once you know the hydronium concentration, you can figure out the hydroxide concentration if you want to. Okay, or you could have used it to figure out the pOH if that's what you were looking for. Okay, so these are some pathways that you might find yourself having to follow in the problems that we're going to do in this course.